altitudes. We're going to have medians and altitudes of triangles. These are the last two different types of segments of triangles and circumcenters of triangles that we're going to learn about. Medians and altitudes. So first off, we're going to have a warm-up exercise like we usually do. So for -4, 8, and 5, 8, find the midpoint. The best thing to do on these is to pause it and see if you get the right answer. But for midpoints, remember those are the coordinates of the point halfway between these two endpoints. So you add these. -4 plus 5 is 1. Divided by 2 is 1/2. And 8 plus 8 is 16. Divided by 2 is 8. I'm going to do all of these and then check my answers. So that's the midpoint. Now we want the length. That's the distance formula. So I'm going to shortcut it here. I want you to remember that you're going to take, I'll write the whole formula for you here. You're going to take x1, you're going to subtract x2, and you're going to square that. You're going to take y1 minus y2 and square that. So I tend to, as I'm doing it, shortcut a little bit. -3 minus 4 is -7. -7 squared is 49. 2 minus -1. 2 minus -1 is the same as 2 plus 1 is 3 squared is 9. 49 plus 9 is 58. Is 58 divisible by, it's not going to be anything with thirds because 8 plus 5 is 13. Is 58 divisible by 2? Sorry, by 4 I mean. Check that. 14 does not go into 18, so I'm thinking that the answer is radical 58. And the last one, for A is 0, 4, C is 18, 4. Find the length of AB, where AB is a point 2/3 of the distance from AC. I don't know if we've done one like this before, but let's think of this, the length of this. Okay. Oh, well, since they both have the same point of 4, correct? Same y value of 4, it's going to be a line 18 long, correct? And 2/3 of 18 is 12. So now I'm going to check my answers. Yay! Yay! And yay! Medians are another type of segment that we can draw in a triangle, and they're going to intersect at a point of concurrency called a centroid. So you'll notice our theorem about medians is only about the point of concurrency, whereas we had theorems about the measurements of perpendicular bisectors, and we had theorems about the measurements of angle bisectors. So a median goes from the vertex to the midpoint, I'm going to color code those, of the opposite segment. So for instance, in the project that you're doing, when you were doing perpendicular bisectors, you already have found the midpoint of the segment. This is not going to intersect though at 90 degrees, so it's going to be skewed differently from the drawing you already have of perpendicular bisectors. It is not going to cut the angle into half. It is not going to bisect it. But you will get a relationship of numbers. The median of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So basically I think of this as in a ratio of 3s. B to P is going to be 2/3 of that length. So from the vertex to the point of concurrency, which we'll find out in a minute is called the centroid, is going to be 2/3 of this. So there's a few ways you can think about that algebraically. You could say, as they did here, that, let's look at BP, which I talked about. BP is 2/3 of BF. The other thing that you could think about is that PF, 2 PFs, is going to equal 1 BP. So those are some ways that you can think about this mathematically. Okay, we're going to now use this concept to solve some problems. As I mentioned earlier, the point of concurrency of the medians is called the centroid, and there's a 2/3 relationship here. SQ is from the vertex to the centroid. That's going to be the longer segment. Okay, so if I divide 8 in half, that's 4. So this QW is 4, and once again that 2/3 relationship. The total length is 12. The longer segment, SQ, is 8. That is 2/3 of 12. Okay, so now they give you a standardized test practice type problem. They give you the vertices, and you're going to have problems like this on your test. I'm going to give you graph paper so you can graph it. Which ordered pair gives the coordinates of the centroid? You could do this from any of the vertexes, but I think they do it from G. So, first of all, since G is going across, it's intersecting FH, you need to find the midpoint. Now on this one, since it's graphed, that's what I like, you could have seen that this is down 2 and over 2, and this is down 2 and over 2. So this would be your midpoint. You actually don't have to use the midpoint formula there. Okay, so when you have this sketched out, you can actually see 1, 2, 3, 4, 5, 6. This length is 6 segments long. 2/3 of that is 4. So once again, I find that the graph paper really helps you out with the problem. Okay, centroid is 2/3, so it is at point, this is 4, 6, looks like 1, 2, 3, 4, 1, 2. Now let's do some practice with what we've just discussed, what we've just learned about centroids and medians. There are 3 paths through a triangular park. Each path goes from the midpoint, so those are your midpoints, to the other end of the opposite corner. So you can see that's going that way, this one's going this way, this one's going this way. The paths meet at point P. If SC, if this entire length is 2,100 feet, find PS. Well, I'm going to go ahead and break this into thirds, and I get that each third is 700. So the shorter segment is going to be S to P, or PS. That's going to be 700. And the longer segment, P to C, is going to be 1,400. So that's P to S, and that's P to C. Let's make sure at almost 10 a.m. on a Sunday morning that I did it correctly. Okay, this problem here. They tell me that BT is 1,000 feet. They want me to find TC and this length here, BC. Well, if this is 1,000, then this, remember this is the midpoint, so this is also going to be 1,000, and 1,000 plus 1,000 is 2,000. So let me check my answer. That is correct. And the last one, there are 3 paths going through a triangular park, so same type of problem. PT, so that right there, is 800. They want me to find PA and TA. This is going to be the shorter segment, so 800 times 2 is 1,600. And if I add 1,600 and 800, I get 2,400. Let's Make sure I did that one right. Yay! Okay, we are now moving on to altitudes. In our prior day lessons, we only learned about one line segment. We learned about perpendicular bisectors on one day. We learned about angle bisectors on another day. Today we're learning about medians and altitudes. An altitude, you've dealt with this before. It's basically the height of a triangle. It is the perpendicular segment from a vertex to the opposite side. I think it would have made it much easier in elementary school if you had just learned this as an altitude rather than a height. You're familiar with this concept. Sometimes the altitude, you would see this drawn as a dashed line. Call it the height of the triangle. Well, guess what? I know you're shocked. All of the altitudes meet at a point of concurrency. You're going to learn in a minute that point of concurrency is called an orthocenter. Okay? The lines containing the altitudes of a triangle are concurrent. Meet at a point of concurrency. So this altitude, this is an altitude, and this is an altitude. And they, in this one, happen to meet right here. So sometimes kids say to me, oh, Mrs. Falk, it's difficult to see this. I get how this line here to here, I see that's the altitude. So now what I'm going to do is I'm going to rotate this. Okay, I want to clear that little annotation there. So what I want you to see here is that this line is now the base. If we extended it, you would hit the altitude. Okay? Remember, the altitude just keeps going. Let me clear the annotations again. And let me spin this again. So now AB is your base. AB is your base. This line would continue out, and you would be able to draw from point C down to make the altitude. As I tell you in your project, you need to extend these lines. In this case, you can see it better here. The point of concurrency, which we're going to learn is the orthocenter, in this case, is outside of the triangle. Okay, so there's some rules here. In an acute triangle, which is what you're doing in your project, P is inside the triangle. That's what you're going to find. In a right triangle, P is on the triangle. Okay? That's the orthocenter from this side. This is really how you would draw it. And if I rotated it this way, here's your other 90-degree line. So they meet right there. In this case, you'll see, yes, the orthocenter is at where the right angle in the right triangle is created. And in an obtuse triangle, it is outside of the triangle. Kind of like compare it to the circumcenter. So we did the very first perpendicular bisector lesson. A circumcenter for an acute triangle was inside the triangle. For a right triangle, the circumcenter was on the right triangle, but it was actually on the hypotenuse and obtuse. Okay, this is going to go through and prove some properties of isosceles triangles. Your book does this proof very differently than what I noticed. So I'm going to try and walk you through how to do this proof. We're told that ABC is an isosceles triangle with a base of AC. Okay, PD is the median of AC. So that's a vertex. It's going to the opposite side. So what I would do first off right now, if you want to try to get better at a proof, is pause this video and write down all of the things that you could say about this. Don't worry about what order they're in. Just worry about what you could say. I'm going to walk you through what I noticed. I noticed right away that D must be the midpoint here. So AD is congruent to DC. I can see that marked. How do I know that they're congruent? Because the definition of a midpoint tells me that they're going to be congruent. And I know that D is a midpoint because they told me that BD is a median. And the definition of a median is that it goes from the center, from the vertex to the midpoint of the opposite side. I also know that an isosceles triangle, okay, has legs that are congruent. That's the definition of isosceles. They've also marked it here. And I know that AB and BC must be the legs because they tell me here that AC is the base. So one of the ways I think the book starts to go through this is to make congruent, I'm going to draw 3 lines there, to make 2 congruent triangles, okay, through side, side, side. And then when they go through the congruent triangles, they end up finding that BDA has to be the same as BDC. And since BDA and BDC are a linear pair, they'd have to add up to 180, and they're congruent, they must be 90 degrees. And the definition of an altitude is that it goes from a vertex to the opposite segment at 90 degrees. I, though, went with something. I have the given there. I said, so they told me it's an isosceles triangle, so AB has to be congruent to BC or CB. That's a definition of an isosceles triangle. The legs are congruent. And I know that AB and BC have to be legs because they tell me that AC is the base. So therefore, since these are congruent, I know that B is on the perpendicular bisector. Fix that. B is on the perpendicular bisector of AC. That's the converse to the perpendicular bisector theorem, because the converse tells me that if a point is equidistant from the endpoints of a segment, then it must be on the perpendicular bisector. So now that tells me that BC is a perpendicular bisector of AC. It also tells me that angles BDA and BDC are right angles, because that's the definition of a perpendicular bisector. Perpendicular bisector, which you've now determined that BD is, will intersect the segment and make right angles. If these are right angles, then this line is also an altitude, because the definition of an altitude is that it goes from the vertex to the opposite side and intersects at a 90-degree angle. And find its orthocenter. So in order to find the orthocenter, I'm going to have to actually use some really nice straight line tools here. This is an example of what you're going to use in your project. Okay? You actually can go to the construction page, and it talks about how to construct an orthocenter. I want to extend these. Okay? In this case, this base is going to stand out. Okay? Which means I would actually need a protractor and a compass to make this exact, but I can actually kind of guess. Okay. It's going to be like right there. And this side here, make sure this is black for the legs. It's easier when I can like rotate it. Extend here. And then this is going to extend out here. So it's going to be somewhere about right here. In your project, you're actually going to follow the link on my website, find the link for how to find the Orthocenter. You're actually going to rotate your paper around to draw it. But this is about what it would look at. In this one, they actually, when they rotated, the Orthocenter is much further up here. That's why I want you doing it on your project so that you can do it exact. Okay. So in example 4, that was our proof. What if you wanted to show that BD is also an angle bisector? How would your proof be different? I think the one in the book actually proved it with side, side, side. So I would still, so in that case, if you went back to that proof, if you remember, that segment here, okay? Okay, so if you wanted to prove it was an angle bisector, you would need to prove those were congruent. So if you did the proof and you did it then by proved this side was congruent to this side was congruent to this side, you could have also said that this side was congruent to this side. So these two triangles are congruent by side, side, side. Then you could prove that this angle, I forget what the letter names are, is congruent to this angle by corresponding parts of congruent triangles are congruent. I have no idea what it says here for what the book says. Okay, so they did by side, side, side. It's the same thing I just said. Okay, so angle ABD would be congruent to CBD by corresponding parts of congruent triangles are congruent. So then BD would be the angle bisector because it made those angles congruent. Set this. Okay, now we have triangle PQR is an isosceles triangle. Yep, and we're bringing in some coordinate proof. So if it's isosceles, okay, this is an altitude, but if these are isosceles, no, those angles are equal. Okay, OQ is an altitude. What do you also know about OQ? Okay, so we talked about if this is isosceles, okay, then we know that OQ is an angle bisector. We know it's perpendicular bisector. Okay, we know it's an altitude, and we know it's a median. We know all of these because isosceles triangles, the vertex angle, so the point from the vertex angle to the base, allows this segment to be all of these. If this is also a perpendicular bisector and it's also a median, it goes through the midpoint. So I know that the P must be equidistant from 0, 0. So if this is H to the right, this is negative H, 0. See what the book says. It says all those things that I just said. And there's your answer. For your daily homework quiz, see if you can do these problems. If BG is 9, find the entire length. Well, half of 9 would be 4.5. So 9 plus 4.5 should be 13.5. Woo! Next problem. If BD is 12, D must be the mid-segment, the midpoint. So AD must also be 12. Woo! And if CD, let's change the colors here. If C to D is 27, 27 divided by 3 is 9, 9, 9. So the longer segment GC here must be 18. Woo! And also find the centroid of A, B, C. So I can use any of these sides. Let's see, this would be down, this would be down, This would be down. Ooh, so that's 4 times. So I can tell that the midpoint of AC is right here. So this is 1, 2, 3, 4, 5, 6 spaces. So 2/3 of that. This would be 4. So this, I'm going to change my color here. This would be where my centroid is. And that is at ordered pair 1, 1. Ooh, the pressure's on. Yay! And which type of triangle has its orthocenter on the triangle? Remember, orthocenter deals with altitude. Do you remember what it is? It is, of course, an isosceles triangle. The wrong thing. They meant a right triangle. Oh, that's so embarrassing. I would not have gotten an A on today's quiz. So once again, remember the same thing with circumcenter. The circumcenter would be inside a scalene triangle. It would be on the hypotenuse of a right triangle. I'm talking right now about circumcenters. And it would be outside a orthocenter would be outside an obtuse. So the orthocenter in a scalene is going to be inside. The orthocenter on a right triangle is going to be right. It's on the triangle right where the 90-degree angle is, and it is outside. And I tell you guys, when you miss a question, that don't just say to me, oh yeah, Mrs. Falk, that makes sense. Actually go through what I just went through. I said it wrong, I knew the answer, but I still forced myself to kind of walk through the steps, and also to help myself, I compared it with the circumcenter, which is the point of concurrency of a perpendicular bisector, because they have the same types of rules. So when you can do that kind of self-talk through it, that's where you know you really know the answer. Let me go ahead and put up, in case you need it, the problems from the, you can see what problems we're doing. Might have added to this. Those are the problems that we're doing for home.